Welcome back, everyone, to chapter number 3, part 2. So, in the part 1, we have discussed network topologies in detail. In this video, we will be covering network technologies, and specifically, we're going to cover the local area network technologies. Network technology definition was already discussed in the previous video. So, we will be talking about Ethernet and the Wi-Fi. So Ethernet, we will discuss the standards of Ethernet and different stuff. And second technology which we use in local area network is wireless local area network or Wi-Fi. So two agenda items for this video: Ethernet, Wi-Fi. We will start with the overview of Ethernet. I'm going to give you detailed overview of Ethernet. Then we will discuss addressing, like how the data travels in Ethernet, like which sort of address it requires. For example, if computer A wants to send a data to computer B, how the data travels, what sort of address we need to append. And then in order to better understand the Ethernet and better understand the addressing, we will discuss the Ethernet frame. We'll discuss the complete structure of Ethernet frame. Then we will discuss the media access. We will discuss how these devices, for example, computer A wants to send a data to computer B, how it can access the media. Like, I mean, it's not like that. If anybody wants to send the data, they can straight away access the medium. No, it's not like that. So we're going to discuss how the media can be accessed. Media mean, I'm talking about the wire or cable or Ethernet, like this cable. So how this cable, this wire, whatever you want to name it, how it can be accessed. Is there a rule or something which we will be talking about? Then we will discuss error handling. Error handling, for example, if there is any error occurs or any collision occur, how to avoid those errors and how we can retransmit those collision signals or something. Lastly, I will discuss some different standards of Ethernet which we use, and there are different type of cables which qualify or which complies to those particular standards. Then we will discuss Wi-Fi in detail. We will discuss the overview. I'll give you a quick overview of Wi-Fi. We will discuss the modes of operations. There are mainly two modes of operation in Wi-Fi. One is called infrastructure. We will discuss that in detail, where we have a central device. The one which we use at home is the infrastructure mode. Second is the ad hoc mode. We will discuss that in detail as well. Then we will talk about the channels, the number of channels plus the frequencies. The frequencies. Like, for example, there are mainly two frequencies over which the access points or wireless routers they operate. One is 2.4 gigahertz, second is 5 gigahertz. So we will talk about it, the difference between these two, the benefit, pros and cons, and applications. Then we will discuss the some different standards of Wi-Fi, the standards, and of course some different technologies which we can use for to compliance with. Lastly, we will discuss these security protocols of Wi-Fi. Okay, so this is the plan for our today's discussion and this particular video, starting with Ethernet, and then we will go all the way to Wi-Fi. So let's start with the first agenda item, Ethernet, and let me give you a quick overview of Ethernet, and then we will discuss addressing frames and everything. So first thing is Ethernet. What exactly the Ethernet is? So Ethernet or this particular standard was invented or introduced by an organization called IEEE. IEEE, Institute of Electrical and Electronics Engineers, they initiated a project 802.3. This is basically where they designed the standards of Ethernet. So interchangeably, in some books, they use IEEE 802.3 instead of writing Ethernet. So under this particular project, they start designing, or they do design the different standards of Ethernet, different innovations of Ethernet are basically performed, or we get it from this particular project. And this standard or Ethernet was invented back in 1983. So just imagine we have been using Ethernet since 1983. And since 1983, Ethernet is one of the most widely used local area network technology. So one of the most widely implemented or used, or you can say implemented, local area network technology, LAN technology. There are many benefits why it is widely used. One of the reason is it is easy to implement, very easy to implement, and the cost of the systems are very cheaper nowadays. It's not that costly, not costly. So no cost, I mean, you can say low cost, not no cost, it's basically low cost. With the ethernet, how much speed we can get with the ethernet, the speed, it varies, depends upon your channel, depends upon which sort of cables, wires you use. But the typical speed start from 1 mbps. It start from 1 mbps, which you guys will not see, of course. It has been obsolete with the previous cables, like minimum is 10 mbps. So starting with 1 mbps, and it goes all the way to 40 gbps. In some books, they wrote it 10 mbps to 10 gbps. Okay, but with the modern category 7 cables are available, so this particular speed ranges from 1 mbps or 10 mbps all the way to 40 gbps. The topology that we use in the ethernet, it basically bus topology that we use. In past, we only use the bus topology to design the local area network by using ethernet. But now this idea has been replaced, and we have started using the star topology. And I believe everybody remember, in star topology we got a hub or a switch and computers are connected with it. In the bus topology, we just lay down a backbone and computers are connected with the backbone cable. Got it? By using the T connectors. So we have already discussed in the last video. So mainly, if somebody asks you in Ethernet which particular topology we use, most commonly, of course, it's the most common is of course star. But again, in past we use the bus topology. Okay, and again, for Ethernet compatibility over network interface cards, over switches, over hubs, they should compliance with the IEEE standard. If you want to use them, they should compliance with that. And again, all these switches and hubs, they do provide you the same data. Let's say if you want to achieve this data, your switch hubs, they should compliance with the IEEE standard. So this is just a small overview of the Ethernet technology, where we use wires, cables, which go, let's say if you use an access point, the cable will go all the way from access point to your PC. Or for example, in the case of, let's say a bus, we will lay down a bus and computers will be connected by using a cable again. Okay, so this is basically a wired local area network. Now let's see the Ethernet addressing, how Ethernets, like in Ethernet, how computers they can communicate with each other. So for communication in Ethernet, computers they need to use the MAC addresses. Uses MAC addresses. MAC addresses. Because this Ethernet is basically a protocol of data link layer. It is the data link layer protocol. Data link layer protocol. So as you know, the data link layer, in the data link layer, we use the MAC addresses, the physical addresses of the devices. So each station for communication. So for communication, if you want to use Ethernet based communication, or for local area network communication, simply because most widely we use Ethernet. So the computers, they need to know each other's MAC address. And how do they find the MAC address? ARP protocol. We're going to discuss this protocol in when we get to OSI model. We will discuss ARP protocol in detail. So it uses MAC addresses for communication, number one, and all computers connected to bus or for example star, they have a MAC address, a unique MAC address. MAC address. Now let me just give you an example how what exactly happens in Ethernet, how they use the MAC addresses. So for example, let's say we are using a bus structure, and let's say I have different PCs connected with this particular bus. Let's say I have 4 computers connected with this bus. This is A, B, C, D, 4 computers. And for example, these are their MAC addresses. A is the MAC address and all. Now, for example, let's say my computer A wants to send a data to D. So if A want to send the data to D, so there should be a destination address. Destination is D and source address is A. When we set the Ethernet messages, Ethernet frames, in Ethernet frames, we will see the Ethernet frames in a bit. Frame, there would be, this is the source destination, sorry, this is not the source, I'm sorry about that. This is the destination, D is over destination MAC address, and this is going to be over source MAC address. So what's going to happen if they are connected with a wire with a bus? So this packet will go to all connected nodes, like everybody will receive it. But now what's going to happen? When this packet or this frame would be received by B will see the destination. If destination matches with this computer's MAC address, then it will open it up, otherwise not. Like this computer will receive the message, it will see what is the destination. Destination is not B, so it will not read the message, open the message. This computer workstation will also get the copy. It will also try to match the destination. Doesn't match, no, it will not read the message. This computer, of course, and this computer will open the message and read the communication. So this is basically how the communication occurs, or that's the way how do we use the communication, the model of communication in Ethernet. Of course, this is the bus. If you incorporate switch, rest of the PCs, they will not get a copy, no copy. If you use a star topology, if we replace it with a star topology, okay. But this is just a simple understanding, so you guys can understand when they open the packet, when they're not. Very importantly, in Ethernet, very, very important thing, no acknowledgement from receiver. So for example, when sender sends the message, let's say if A sent the message to D will not send acknowledgement. So there is no acknowledgement mechanism in Ethernet, and Ethernet totally relies on network protocols to ensure delivery. So for example, if the package has not been received, but there would be no acknowledgement. For example, if there might be a collision or something, D will discard the packet. In Ethernet, we mainly use encoding scheme. Encoding mean, for example, if you want to send the data 1010 and all, how do you send the data? We use an encoding method which is called Manchester encoding. We will not discuss the coding in this chapter, but if you would be interested, I'll give you overview of Manchester encoding in the class. So what we have discussed Ethernet. When Ethernet was invented, this maximum, minimum speed, topology that it used, and addresses. So the bottom line is Ethernet uses mainly the MAC addresses for communication with other devices. Now let's come to, so this is the Ethernet frame. If you guys see, there are different fields like preamble, SFD, which is start frame delimiter, destination address, source address, length, data, CRC, cyclic redundancy check. So all these fields are added on different layers, like for example, preamble and SFD. These fields are called mainly the physical layer header. Why we call it physical layer header? Because these two fields are added at physical layer. So these are basically called PL header, physical header. The length of preamble is 7 bytes, which is 56 bits. And the length of SFD is only 1 byte, which is 8 bits. Destination address, source address, length, and even CRC, these are added on the data link layer. So we call them DLL header, data link layer header. And the destination address, which is basically destination MAC address. Similarly, the source MAC address, we have already discussed that in the Ethernet, we use MAC addresses for communication. So destination MAC address, the length of the destination MAC address is 6 byte. 6 byte for the source MAC address, and length is only 2 bytes, by the way. CRC, the length of CRC is 4 bytes, okay, which is for error detection. In fact, basically it checks the vandalism, like for example, any sort of for example, modification, accidental modification, collision, and these kind of things. Length, the length of this data is basically variable. The length of data is variable, where the minimum length of the data, it ranges from 46 bytes to 1500 bytes. Like it's not like that you can add as much data as you want. That's the limit in Ethernet. You cannot actually go beyond that. The minimum length of our Ethernet frame when it leaves the data link layer, the minimum length of the frame minimum length should be 64 bytes. This is basically the rule, like this is what is defined in IEEE 802.3. This should be the minimum length of the frame. We will discuss that, we'll calculate all these fields. First of all, we need to understand all these fields. What is the role of these, like preamble, SFD, and all these fields? What are the roles of all these fields? So let's start with the first one. Let's start the preamble. Preamble and SFD. SFD. So SFD, what is SFD again? Starting frame delimiter. So these two fields are basically fixed. These are fixed, which are added on physical layer. When the frame get to the physical layer, these two fields are added, and these two fields has nothing to do with the information. These two fields, they just use as an alert. They just alerts that frame starts from here, or you can say frame is gonna come, or frame starts from here. You can say frame starts from here. Okay. And how the preamble look like preamble, which is basically preamble, as I mentioned earlier, preamble is of 7 byte. It means 56 bits. 56 bit, because 7 multiplied by 8. So 56 bit, and how it will look like 10 10 10 10 all the way, this pattern. Similarly, SFD. SFD also follow the same pattern, which is of 1 byte only, 8 bits. And it looks like 10 10 10, but last two bits are 1 1. Why we use the last two bits are 1? They basically tells the end of delimiter, or it basically avoids the confusion between the DLL header and the physical layer header. So 1 1, it mainly tells delimiter, or you can say physical layer header. It ends here, like the alert ends here, and the next is, of course, is going to be the DLL header, where we have the source and destination MAC addresses and other stuff. So just to avoid the confusion, like there is a destination MAC address, this is separate than this particular part, which is the PLL header. Next, we have the destination address and source address, which are the MAC addresses of source and destination. And why it is very important? The reason is that this is the actual data. Typically, we don't want the others to open the data. And let's say, for example, we are using a ring methodology, ring topology. For example, we have different workstation connected with this backbone ring, the bus. Let's say this is A, B, C, and D. A wants to send the data to, for example, C. A wants to send the data to C. So what's going to happen? The packet, the frame would look like this is the source address, the destination. This is destination, and that's the source. Destination is C, and the originator or source is A. This is basically what would be added down here. Okay, so this particular frame would be received by all these stations. This will also receive a copy. It will also receive a copy. It will also receive a copy. Now, what's going to happen when this particular frame, like this frame having source and destination address with this, will get to this particular workstation? The workstation will see and try to match the destination. Like here, the destination is C, and this computer MAC address is B. It will not further open the packet. It will discard the packet. It will not read it, because it will say, hey, it's not for me. When this computer will receive this particular frame, so what's going to happen? Since it matches, so it will open it up, and this computer will also not read the message, because it is not meant for that. So this is basically why we have the source and destination MAC address and their role. Length, which is of the 2 bytes. 2 bytes means 16 bits. So it's going to be 16 bits. This is just the padding. And why we put the padding? Just to separate with data. Like data should not get confused with the source and destination addresses. Okay, MAC addresses. CRC, cyclic redundancy check. It's just, we use it for error checking, error verification. Receiver mainly use CRC to see whether the frame has been altered or not. Okay. We will discuss CRC. There are different algorithms in CRC that we use. If you would be interested, we can discuss that. Although it's not a part of our course, but we can talk about it if you are interested. Now let's see why we use, why is the minimum length is 46 bytes, and why 1500 bytes is the max limit of our frame. Okay. So first of all, let's start with that. So let's say if I draw a small table that will make more sense to you all. So let's say this is our data, and for example, what is the minimum size of the data, and let's say what is the maximum size of the data. And let's say this is the frame. Frame is I'm basically using the frame which is at the DLL. These are basically the layer, the physical layer component has nothing to do with the data or for example with the frame, but this is just like alert. So I'm just considering this one, and that's what most of the books they actually do. So if you guys, for example, calculate the frame size. So as I mentioned earlier, the minimum frame size should be 64 bytes as defined by IEEE 802 point standard 802.3. So it should be 64 bytes. So let's see what would be the data size. How do we calculate it? You want to design a frame. So we will add 6, for example, this 6 plus 6, this 6 plus 2. Let's say we don't have data, we want to calculate that, and plus 4. So 12, 14, 18. So it makes 18. So 64, which is the maximum length, minimum length, minus 18 makes 46. So this is where the 46 bytes of data comes from. So if you want to send a frame, this should be 46 bytes. Let's go to the maximum one. So the maximum size, we have already talked about it. It should be 1500. I mean, you can calculate that, the maximum 1500 bytes. So what would be the maximum frame? Add those 18, of course. So 15, 18, like those 18, like these 18, the rest remaining fixed components. So this is basically the max and the minimum size of the frame and the data as well. Okay. So that's basically what the frame is, and this is how the Ethernet frame looks like, which will travel through the Ethernet cables. Okay. Now let's talk about how the workstation, they can access the media. So first of all, let's say if I have a computer, let's say if you see, this is basically the bus topology, and let's say A wants to send the data to, let's say D. A wants to send the data to D. So if A and D, because they are connected, if you guys see, this is a bus and that is a common carrier, common channel, you can say carrier, common channel. Okay, so everybody is basically sharing this particular channel for communication. Now, what is going to happen? Let's say if A wants to send the data, A sends the data to A wants to send the data to, let's say, D, and in the meanwhile D is also sending back to data to for example A, and for example B is also wants to send the data. So what's going to happen? There would be a collision. There will be a collision. All these computers, their signal is going to collide. So the problem is, because by default these stations, they want to transmit the data, whatever the data they got, they want to transmit the data. They don't care whether other people are sending the data or not. So the problem is how we can use how we can allow the workstation to access the channel. So there should be no collision. In order to do that, to control the access, in Ethernet we use CSMA with CD. What it stands for? It stands for carrier sense multiple access method with collision detection. So what this particular method is? The method is, for example, if any workstation want to send the data, first of all, they need to sense the channel. They need to see that if the channel is freely available or not. They cannot straight away send the data. For example, let me give you a simple example with the same example. So for example, let's say I have again those 4 computers and connected with a bus. This is, for example, A, B, C, and let's say this is, for example, D. A, B, C, and D. So, and they are connected with this T connector, as you know, the connector node. So what is basically the idea? Idea is that if A want to send the data to D, they cannot directly send the signal. Let's say A send the data to, for example, D, and D also in the meanwhile send the data. So what's going to happen? There would be a collision. We don't want this collision. So how we can avoid this? In order to avoid this, we came up with the idea, and idea is CSMA, the carrier sense multiple access. How we can do that and how it's gonna work. In order to avoid it, what's gonna happen? If A wants to send the data, first of all, A will use this particular connection and sense it. sense, or you can say it will try to see whether it tried to see, for example, if any other computer is sending the data, like it is getting the data on this particular channel or not. So for example, A just sense it, check this out whether there is any sort of presence of data or something. A will basically, now if this is free, it means A will assume that channel is free. A will start broadcasting the data. But stop here. I mean, there's a problem. What is the problem? The problem is that D is also sensing its channel, like this connection, and D find, hey, there's no channel. I mean, there's no signal. Everything is fine. D also start sending or creating a signal. Now, what's going to happen? Of course, because they cannot see in advance, like A cannot see the data may be traveling here, data may be traveling here, right? So A just checked it out on its own side and it found there is no presence, no signal. So it transmitted a signal. Now what's going to happen? This is carrier sense. Carrier sense, this is CSMA. They are sensing the channel. This is CSMA. So when they send these signal, again, what's going to happen? There would be a collision. When there will be a collision, everybody will, like this computer, all the workstation, they will get a collision signal. They will get a collision signal. Collision signal mean they will get the idea like somebody has collided. Somebody's signals or traffic has been collided. But question is again the same. Like CSMA idea was really good, but it does not avoid the collision. It does not detect there would be a collision or not. Because again, if A's data was involved, A need to retransmit. How A would get the idea whether A or D's data was involved in the collision? How it can get to know that? In order to do that, we modified CSMA with the collision. We modified this CSMA with collision detection module, where we have defined, like for example, the length of the packet, the length of the frame should be, again, we have discussed that the frame length should be 64 bytes to 1500 bytes. If it would be of this particular length, and there is a formula for that as well, which is basically like the length of the frame should be at least greater than equal to twice of the transposition propagation multiply with the bandwidth as well. You don't have to go in that complexity, okay? I'll explain you if you guys would be interested. So this is basically what the frame length is. What exactly the point is? The point is that, for example, A sensed, for example, the channel, and A found there nobody sending the data. So A will generate a packet like this length. A want to send the packet or this particular frame to D. Then that's the length of the frame. Like this is basically the total length of that particular frame. Now, in the meanwhile, when it was about to send, D started sending the data. And this was the D started the data. Now, D has started sending the data. Now, what's going to happen? They are going to collide for sure. There would be a collision because D detected there was nothing on it. D started sending the data because D sensed it and channel was free. When this collided down here, now what's going to happen? This collision signal will travel back to A. This is the collision signal. Collision signal. Now, everybody will get it. Of course, this particular station will also get it. This particular station will also get it. There is a collision. But they were not transmitting anything, right? So they will see that, yeah, I have nothing to do with it. I have nothing to do with it. But now what happened? There was still some data which A was transmitting and it got the news of the collision, like collision signal. So A got it like, I have to retransmit it. I need to retransmit my signal again. Why? Because there was a collision, like somebody else was also sending the data. And D will also, because there was a signal will also be transmitted to D. D will also, because there are still some data to be transmitted, D also got the collision signal. D got it. I have to retransmit it. Got it? This is basically CSMA with the collision detection, where we have defined the packet length. The frame length should be enough, should be long enough, at least where we have decided 64 to 1500 bytes. So what should happen if there would be a collision? So we can also, the stations can detect it. The collision can be detected. plus collision not only detected, but we can be able, because once we detect it, then we can retransmit, because there is no acknowledgement mechanism, right? We have already talked about. So collision detection tells us whether receiver got it or not. If there would be a collision, we got a collision signal and we are not sure whether it is for us or not. So if we have a sufficient length of over packet, over frame, then we can transmit the data, retransmit the data in the meanwhile. So this is, by the way, what media access control is. How access control, how the stations, they can access the channel. They just have to sense the node, and once, for example, they find the channel is free, they will transmit the data, and the length of data will define. If there would be a collision, it will retransmit it. So the next is the half duplex versus full duplex. We have already discussed half duplex. Half duplex. There is another one which is called simplex. So we have simplex, we got half duplex, we got full duplex. Simplex is basically like simplex is like, for example, the radio. Radio, what is radio? Radio is like, for example, only one way. It's just like one way communication. One way communication mean only one person, which is sender, can transmit the data and you will receive the data. While half duplex is two way, but one at a time. Like, for example, walkie-talkie. Just like walkie-talkie. And what is walkie-talkie? Like, for example, you'll say, sender will send the data to receiver, and receiver has to stop. Receiver cannot simultaneously transmit it. And when receiver will become the sender, so this sender will become the receiver. So there would be only single channel. Full duplex mean sender and receiver both can simultaneously communicate. Full duplex, like there are two channels. So typically over hubs, if you use a hub for star, you make a star network. Hubs are basically, they use half duplex, and hubs, they use CSMA, collision detection, in order to avoid collisions. While full duplex, it's switches, they are usually full duplex devices, and there is of course no need of CSMA, no need of the carrier sense multiple access collision domain. There is no need for that because they can communicate simultaneously, and there would be no chances of collision. Okay. So the last thing for today for the Ethernet is the Ethernet standards. For Ethernet, first of all, we can use different. If you want to design an Ethernet, so we can use different sort of cables. We can use coaxial cable. We can also use the category 5, category 6 Ethernet cable. We call it Ethernet cables, which are basically, the technical name is UTP, unshielded twisted pair cable. We have already talked about in the last video. Or we can also use the fiber optics, okay, in order to design the a simple Ethernet channel, Ethernet network. This is basically the standards which IEEE, they have designed this particular standard, like X base Y, where what is X? X is basically, X defined basically the distance, like the data rate. X defined the data rate, while base B is, it tells this is the baseband signal. Baseband signal mean original signal. There is a band pass signal as well. Baseband mean original signal, original. Like, for example, whatever the original signal at low frequency is, pass through the channel. While this Y, it tells two things mainly. Sometimes we use distance, okay, like, for example, I'm going to explain you in a bit, or it can also be used with the description of the cable, which sort of cable, which sort of channel we're going to use. For example, there are different examples for that. Like, there is basically a standard 10 base T. What does it mean? So in Ethernet, basically we use three main standard. One is called standard Ethernet. Ethernet can be fast Ethernet, or Ethernet can be a gigabit Ethernet. Okay, standard Ethernet, if you talk about standard Ethernet, it is basically 10 Mbps. If you are getting the data rate, if your data rate is 10 Mbps, that is standardized Ethernet. Fast Ethernet is basically where you're getting up to 100 Mbps data rate. Gbps, 1000 Mbps or 1 Gbps. And we know that in Ethernet, there is a possibility we can achieve up to 40 Gbps. Okay, so 10, let's come back to the standard. So first standard, which is kind of obsolete, by the way, 10 base T. So it means 10 Mbps data rate, baseband signal, and T is, it tells it is a twisted pair cable. Sorry, it is the twisted pair cable, which is basically the UTP, unshielded twisted pair cable, like where we have the four basically four pairs of the cable. So and 10 base T, this is one of the standard. Previously there were, and again the range of this one is only 100 meters. So 100 meters is basically the maximum range where you will get the data of. So 100 meter is the maximum range twisted pair cable, 100 meters, and maximum speed would be 10 Mbps. Okay, that you from end to end, this is maximum speed that you can get. This is basically what this standard is. So I'm going to actually tell you all these standards with a category and other in the other sense as well. But these are basically the different standards. One of the standard was 10 base 2. So 10 base 2, if you see that one, it means this is 10 Mbps, and it tells baseband signal with can travel up to 200 meters. So this sort of cables, if you design it, it can be of course achieved with coaxial, category, or fiber, but typically it's the unshielded twisted pair cable, the one which we achieve it. So it is called a thin cable. Another standard was 10 base 5, which is kind of thick, which is basically coaxial cable. So it can cover up to 500 meters distance. Similarly, we have 10 base FX, which is basically fast in fact, and it's basically the fiber optic. So FX, that's basically fiber optic. It is fiber optics, which is faster. And similarly, there are other standard as well. I'm going to actually give you some standard which are important from exam point of view, and which you should memorize, you need to know. I'm going to actually write it down here. Let me see if I have, okay, let me add a new page here. Let's see. All right, so we're gonna, let me add a new page here, and let's put it down here. Okay, so some of the standard which is basically we achieve with the category 3 cables, and that is basically 10 Mbps. With the cat 3 cable, maximum data rate is 10 Mbps, and it complies with the standard 10 base T, which I told you this is the IEEE or Ethernet standard, and which cable complies with cat 3. Then cat 5 cable, where we have 5 pairs, and again maximum data we can achieve is 100 Mbps and standard 100 base T. So of course you guys can see here only the distance is 100 meters. Okay, then we got another extension of category 5 cable, and we can get up to 1000 Mbps, and this is 1000 base T. Okay, then the category 6 cable, which basically provide up to 1 Gbps and 1 Gbps data rate, and this is again 1000 base T, compliance with 1000 base T. And again, this distance could be 55 meter if, for example, it is providing 10 Gbps rate. So if you for example use the same standard, the range would be 55 meter. Typically the range is 100 meter, but if you use the same standard, and you are getting 10 Gbps, so this is what you'll get, the distance would be short. Similarly, the category 7 cable, it offers 10 Gbps speed, and the distance is 1000 meter, up to 1000 meter. So the minimum, for example, the minimum cable category through which you can get the 100 Mbps is category 5. So you need at least cat 5 cable in order to get that. And the maximum distance of UDP category 5 cable is, I mean, this is 100 meter. We call it 100 meter, but practically it is 99.97, and then it would be fully faded. That's the maximum distance which it can travel. In fiber optics, of course, as I told you guys, we can also use the fiber optics here to design the Ethernet. And in fiber optic, there are different type of cable. We will discuss these cable in the next chapter. One is called single mode cable. There is another one which is called multi-mode cable. We will discuss these single mode, multi-mode fiber in detail. But for long distance communication, just remember, long distance we use single mode cable. In multi-mode cable, basically it's thicker and there are multiple signal are traveling. Okay, so if multiple signal are traveling, there would be more interference. We will discuss that in detail in next chapter. In single mode cable, we have multiple cables, but each cable is carrying only single signal. Okay, so that is why there would be less interference and less fading. That's why single mode fibers travel up to a longer distance. So this was all about Ethernet. We have discussed standards. We have discussed their communication model of different devices, Ethernet frames. And now let's talk about the last agenda item, which is the Wi-Fi. And the full form of Wi-Fi is wireless fidelity. So Wi-Fi was introduced back in 1997. Again, the same institute, IEEE, Institute of Electrical Electronics Engineers, they came up with that, and the project number was 802.11. So what was the idea of Wi-Fi? Previously, what was happening? The idea was like, for example, this is your computer, and that's, let's say, your local area network, and you are connected with, for example, a hub or a switch, and that particular switch is connected, for example, with your ISP router and all that. Let's say we got router and other stuff. So let's say this is our local area network. So what was the problem? The problem is that it restricts your mobility. Like, for example, if you want to use internet, you have to be connected with the Ethernet cable. So idea was that if we, for example, remove this cable, if you want to remove this cable, and remove this particular switch as well, let's remove this switch or the hub with such access point, which is basically antenna base, rather than just a wired one, like a wired port, it should have some wireless ports. And here, if you see this particular computer, their network interface card must be replaced with some sort of antenna. So rather than sending the signal through the wires, if we start sending the signal wirelessly, okay, so the problem is, or the biggest challenge, and again, it will support the mobility. You can actually move anywhere you want. You can sit, for example, on the bed or wherever you want. No wires are required. But the problem was that why people didn't adapt the technology straight away? Because of sniffing. Like, there might be few people or the bad guys in your local area network, they can start sniffing your packets. They can see whatever you're transmitting. We will see that. We will discuss that, how this problem got addressed. So this was the biggest challenge. And then, of course, the cost of wires at that time was higher, of course. And one of the reason why we went to the Wi-Fi technology, the idea was to reduce the cost. As well, rather the cost of the wire. Even though the wires are getting cheaper and cheaper, but we'll talk about it. So this is the main idea of wireless fidelity, or you can say Wi-Fi, and also called WLAN, wireless local area network. So first of all, let's talk about some modes of operation. In Wi-Fi, there are two modes of operations. So there are two modes of operations, the way how Wi-Fi actually works. One is infrastructure mode, and second is ad hoc mode. So infrastructure is basically where we use a central device. Like, for example, let's uses centralized device. So for example, this is over a hub or a switch and couple of devices connected with that. Okay, wirelessly, of course. Let me draw this again like this. For example, we got access point and couple of devices connected with it. Okay, using the one which you guys use at your home. Ad hoc based, there is no central device. It is basically peer-to-peer networking. Like, for example, your hotspot that you guys like, for example, the hotspot we create, one of the examples. Second is, for example, the buses, like where we deploy the bus, the bus, and then devices are connected with the bus, something like that. That's basically another idea of that. We will be discussing this infrastructure based in this video, and of course ad hoc based. If you will have any question, we can discuss that in our class. But our book has mainly focused on the infrastructure based. So first of all, how the communication occurs in the wireless local area network. So communication occurred through the frequencies. So, and there are two main frequencies in the Wi-Fi. One is basically 2.4 gigahertz. Second is 5 gigahertz. Let me zoom it. All right. Second is 5 gigahertz. So most of your Wi-Fi routers nowadays, they are called basically dual band routers. Why we call it dual band routers? Because they do operate on 2.4 gigahertz plus 5 gigahertz. Now, what is basically a frequency? Frequency is basically the characteristics of a signal. Like for example, when you say something, speak. The human speaking ranges, let's say when we speak something, the human speaking ranges, it start from 300 hertz all the way to 3300 hertz. So just imagine it is very, very high frequency in gigahertz, billion hertz. Are you getting a point? 2.4 billion hertz. So when we change human frequency to this is basically called the modulation. And when the signal 300 hertz, let's say, just imagine you are basically, I mean, how fast you can travel. You can walk. Maximum, I mean, for example, if I ask you, can you please get to campus from your home? So while walking or running, so for example, if you live in Alpharetta to Lawrenceville, how long it's going to take? If I ask you to go, I mean, without any ride and without anything. So it's going to take maybe 1 to 2 hours. Even though if you, for example, run. But for example, if I ask you to take a Uber or a cab, or maybe you can come on your own ride. So it's going to take maybe 30 minutes or maybe less than that. Are you getting my point? So 30 minutes because you are on the fast carrier. This is called your carrier in technical terminology. So 30 hertz would be superimposed on high frequency. Exactly the same way whenever we try. So this is called a baseband signal. Now I believe everybody got the idea about baseband. Low frequency signal, original signal. And this is when we superimpose on the high frequency, it is called band pass. So at 2.4 gigahertz, when we transmit the signal, 2.4 gigahertz offer 14 channels. And each channel is basically separated by 5 hertz. Just forget about it. 2.4 gigahertz, it has more interference with your household items. For example, your microwave ovens, for example, walkie-talkie, etc. So it does get some interference. 5 gigahertz, it is better than that. 5 gigahertz, at 5 gigahertz, it offers 42 channels. And again, less interference as compared to 2.4 gigahertz. Now let's try to understand what these channels are. So for example, this is my access point, and assume that this access point operates at 2.4 gigahertz. Channel is just like TV channel. Okay, just like TV channel. So it is, for example, 2.4 gigahertz, even though it offers 14 channel, but you know what? The usable channels are only 3. Even though it offers 14 channels, but usable are 3. But right now, just imagine we got 14 channels, just for the ease. We have 14 channels, for example. So what does it mean? It means virtually it has 14 wires. 1, 2, 3, up to 14 wires. These wires are not visible. Like it doesn't look like again, you don't see them, but there are 14 wires. So for example, this is you. And let's say there is another person as well. If you want to send the data to, for example, you want to send your data, let's say you got this data, you want to send the data to, for example, to the access point, you will send the data on this channel. Are you getting a point? So let's say 14 channel, you will pick this channel and send the data, and this data would be received by access point. So channel is just like virtual wires. So channel, what is a channel? Virtual wires, which you cannot see. Are you getting the point? And there is a possibility of collision. Of course, there is a possibility of collision. Why possibility of collision? Let's say, for example, 14. A was sending the data on, let's say, channel number 1. and B also try to send the channel on 1. So now what's going to happen? There would be a collision. And the problem with the air is no collision detection. There is no collision detection. So how we can avoid it? We can basically use CSMA, collision avoidance method. CA, so it is carrier sense multiple access with collision avoidance. And how do we avoid it? Very simple. Let's say if this computer A wants to send the data on channel 1, first of all it will send, you remember CTS and RTS, like RTS is request to send, and then when it gets CTS, so firstly it will make a handshake, send RTS, request to send, and then it will receive CTS, clear to send. It is, what is that? It is basically sensing. It is sensing, like they are basically very sure this channel is not occupied by any other computer. This is basically CSMA, the collision avoidance method. Okay, so this is the way how, and these are the frequencies, the way how the channels or signal can be transmitted. Now there are different standards of IEEE. The one which we use, the first standard was 802.11. It's basically called 802.11b. Okay, and that standard, the data rate was 11 Mbps. It's IEEE. In fact, IEEE 802.11b, and frequency is 2.4 gigahertz. So at 2.4 gigahertz, this is the standard was proposed by IEEE, maximum 1100 Mbps. Other standard is 802.11a, and you can get up to 54 Mbps data rate. And here the frequency is 5 gigahertz. So you guys can see with 5 gigahertz, you're getting more capacity, more bandwidth. So it offers you more bandwidth. It doesn't mean that 5 gigahertz offer more bandwidth, because the bands are wider. Like you can get the same bandwidth with 2.4, but channels are small. So channels are small here. So that is why, like for example, the channel width, the virtual wire width. Similarly, another extension or the standard is 802.11g, and that's also offer 54 Mbps, but with the 2.4 gigahertz. Another standard is 802.11n, which offers 65 to 600 million bits per second, bits per second, and you can use it at 2.4 gigahertz and as well as 5 gigahertz channel band as well. Why this data rate is so fast? Because it offers plenty of features. One of the feature is MIMO, multiple input, and multiple output. So multiple input, multiple output. So your network interface card of your device and your switch and hub should actually compliance with this. So it should have multiple antennas transmitting the same signal. Okay, so in our transmitting the multiple signal, let's say we got a signal having 3 frames, 1 2 3, so all the 3 frames would be transmitted together. That's why you achieve the higher speed, because previously there was only one antenna. If you want to send 3 packets or 3 frames, 1 2 3 at a time, only 1 frame will be transmitted. By using multiple input, multiple output, sender and receiver, they have multiple antennas. So the signal or the frame would be transmitted, like this will transmit frame number 1, 2, and 3. So speed would be 3 times more as compared to the previous one. Other than that, it also offer another thing which is called channel bonding, frame aggregation. These are aggregation, and these sort of things have been embedded in it. Another standard which which is basically the modified form of MIMO, which is called 802.11 AC, and it basically offers up to 1.3 Gbps. Okay, again it operates on 2.4 gigahertz, 5 gigahertz, and even 5.08 gigahertz as well, which is of course one of the channel of 5 gigahertz. Here they use a MU, which is multi-user MIMO. Multi-user MIMO, like multiple users can also be communicated with the same signal strength. Then we have 802.11x. This is basically famous for network access because here the authentication of the network was improved by using security certificates. So security certificates were basically incorporated in order to improve the security as well. The biggest concern, we do have a concern, security concern with the Wi-Fi or the local Wi-Fi devices, the Wi-Fi access points. The reason, because they can be sniffed and go in order to protect or provide the security. There are different security standards they came in. Like first security standard was WEP, wired equivalent privacy. So this was the first security standard, wired equivalent privacy, and it was designed back in 1998, right after 1 year of Wi-Fi introduction. The best thing was it offers encryption. So it does offer you encryption, but it does not offer the access control. Like everybody can access your access. Like for example, the data from this computer to access point goes in an encrypted form, but everybody can access to your access point. Then later on, another protocol came in, which is called WPA, which is Wi-Fi protected access. So what was Wi-Fi protected access? Wi-Fi protected access, it offers encryption. Not only encryption, beside encryption, they also provide you the access control of the device. Access control, you can say the pin or the password, the Wi-Fi password. It came in. Let's say if anybody wants to get connect, there is a password for that. Encryption algorithm was not that great. It's better than this one, but encryption algorithm was a little bit weak. Okay, it was better, but encryption scheme was not that great. Then WPA2 came in. Okay, the WPA2 for encryption, they use AES encryption. And there was another method which was PSK. Basically, it's the user encryption key. Again, the same method for access control. Access control was incorporated. It was basically the strong and the best method that we use. For enterprise, we have a WPA and the WPA2. Enterprise. And this particular method is basically use authentication server. Authentication server. One of the servers, Radius. There are many different servers, TAC, ACS Plus, and others. For example, how it looks like. Let's say if this is your cell phone, you want to connect with their access point. So what happens? The passwords are not stored down here. So what happens when you try to connect with that? It will forward your request to the server. Okay, and you will see basically a form like a web page. You'll see a web page where you need to add, for example, your username, password, or for example, you need to add the room number or something like that if you are accessing in a motel. So that's basically how the WPA2 is integrated. So once you put username password, username password will go to access point. Access point will forward it to Radius server. Remote authentication, dial in user server. Server authenticate you and give a green signal like, hey, allow it. And this user will be able to access the access point. So that's it about chapter number 3. If there would be any question, please bring it up in the class.